This is where we left off in Chapter 4. We were talking about oxidation states and redox reactions. So let's look at how we identify redox reactions. To review, oxidation means that there's an increase in the oxidation state of a substance, usually an element. Oxidation means loss of electrons. Reduction means a decrease in the oxidation state, which corresponds to a gain in electrons. So if we look at this reaction between carbon and sulfur, these are two nonmetals. They're forming a molecular compound. There are no ionic charges to tell us what lost or gained electrons. And so this is where we need to use the oxidation states. So we identify the oxidation for carbon as 0 because it's an element. The oxidation state of sulfur is 0 because it's an element. Then in this compound, we have to apply those rules. It comes down to Rule 5 and that table, Fa 765. So no fluorine, no hydrogen, no oxygen, no group 7, but sulfur's in group 6. So sulfur gets to be -2. There are 2 sulfurs, so that's a total of -4. Then there's 1 carbon, so the oxidation state of carbon is +4. So after doing that, then we look at how the carbon's oxidation state changed. It went from 0 to +4. That's an increase. An increase in oxidation state tells us that the carbon is oxidized in this redox reaction.
How do we know that carbon is +4 for sure? Can it also be -4? Is it because
No.
it's reacting with the sulfur?
It's in this compound, it's a neutral compound, and so all the oxidation states of the elements present have to add up to 0.
Okay.
So it has to be +4. There are other compounds where carbon could have an oxidation state of -4.
Okay, it's just based on where the elements are.
It's based on what the other elements are there. And like I said, this is a made-up device to help us recognize redox reactions. It doesn't correspond to a charge. Carbon does not have a +4 charge in this compound. It's not an ionic compound. So the carbon is oxidized. The sulfur went from 0 to -2, a decrease in oxidation state, and so that means that it is undergoing reduction. Any questions? If there's oxidation, there has to be reduction. If something is losing electrons or losing electron density, something else has to be gaining electrons or gaining electron density. They always go together. So let's practice this. It says use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. So they're telling us up front we're going to need oxidation states. So the first thing to do then is to go through and identify the oxidation state for each element. So this tin, what's its oxidation state? 0. It's an element. All elements have oxidation states of 0. And here we have nitric acid. So we've got hydrogen, nitrogen, and oxygen, 3 different nonmetals. So we have to use Fa 765. There's no fluorine, but there's hydrogen. That's the second priority. Hydrogen gets to be +1. Next is oxygen. The oxygen gets to be -2, because that's what it wants to be. So what does the nitrogen end up being?
+1.
No, neither of those. Let's look at this. So we've got +1 from the hydrogen, and let's just call the nitrogen's oxidation state X for now. And then we've got 3 oxygens, and they're each -2, and all of those have to add up to 0. So we've got +1 plus X, -6 equals 0. So what's X? +5. So the nitrogen is +5. Okay? So, if you haven't been paying super good attention, you look at that and you're like, oh my goodness, this is just all crazy stuff. It's the same idea as if you got some people together for a meal and you're trying to split up the check. And it's like, okay, I put $20 in, but your check is this and your check is that, and you just figure it out, okay? It's just simple math. It's plus and minus, but it can be confusing. Don't let the confusing part just make you give up on it. It's not hard. You can figure it out. These charges have to add up to 0.
And why are we doing it specifically for 4HNO3? Is it because we're doing it for the reactant?
We have to do it for everything.
Okay.
We just haven't gotten to the products yet.
Okay.
Okay, so any questions about the HNO3 one? The coefficient 4 has nothing to do with anything right now. Doesn't come in at all. So then let's look at this one, tin oxide. Well, here we have a metal and a nonmetal. And so we know that the charge and the oxidation state are going to be the same. What's the charge on oxygen? -2.
Where did you get the X from?
That's the oxidation state for nitrogen, what I'm trying to figure out.
So then where's the 5 coming from if that's
X
not
equals 5. So if I rearrange this, I get X equals +6 minus 1, which is +5. So in here I'm saying here's the oxidation state from hydrogen. It's +1, there's only one of them. I have 1 nitrogen, I'm going to call it X because I don't know what it is. I have 3 oxygens and they're each -2, and I know that all of these have to add up to 0.
Okay.
And so then I'm going to just solve for X, and X is 5.
And why is it 0 then?
Because this is a neutral molecule, it doesn't have a charge overall.
Okay.
If it was a polyatomic ion, then all the oxidation states have to add up to the overall charge.
Okay.
So in tin oxide, I've got 2 oxygens. They're each going to have an oxidation state of -2. They have charges that are 2 negative. What is the charge on the tin? +4. And so then the oxidation state is also +4. Because for monatomic ions, that compound is those 2 ions. So for monatomic ions, the oxidation state is the same number as the charge. So here we have NO2. We can't just say, oh, well, the nitrogen's 5 and the oxygen's -2. Because the nitrogen was 5 as a reactant, but it might be something different over here. So we apply the rules, and oxygen comes before nitrogen, and so the oxygen gets to be -2. What's the charge on the oxidation state of the nitrogen? Yeah, it's +4. There are 2 oxygens, so 2 times -2 is -4. -4 plus +4 adds up to 0. Excuse me. In H2O, the FHO, H gets to be what it wants, priority over oxygen. And so what's oxygen here? -2. There are 2 hydrogens, they're each +1. That's a total of +2. And there's 1 oxygen, +2 minus 2 equals 0. Okay, any questions about how we got the oxidation states?
For the tin,
Mm-hmm.
for tin and oxygen, why is, or no, for the nitrogen, why is it +4?
Because the oxidation numbers of these things have to add up to 0.
Okay.
And so we've got the oxidation state of nitrogen is +4, and then we have 1 oxygen that's -2 and another oxygen that's -2, and that adds up to 0.
So it's just based on the math because
Yes.
there's 2 oxygens.
Yeah.
And
So we look at 2 oxygens. The oxygen won the draft. It got its first pick, which is -2,
Yeah.
and then the nitrogen has to be whatever works out.
Okay.
molecule you said the hydrogen takes priority?
Yes.
So that means that, let's say it was OH instead, would the hydrogen still take priority?
We've got that, the list is FHO765.
Okay.
Those are the rules we made for determining oxidation numbers, and there's science behind it. We didn't just make it up. But fluorine has first priority, then hydrogen, then oxygen, always.
And then, so like they say, if it was still OH, would that mean that the oxygen just has a
Yeah,
negative?
if we had OH without a charge, the hydrogen would get to be +1 and the oxygen would be -1. There is no such thing, but that's what it would be.
Hydroxide.
Hydroxide has a charge,
Oh, yeah.
which makes the oxygen -2. Yeah. Any other questions about how we got the oxidation states? Okay, let's answer the real question now.
Will it always equal 0?
It will always equal the charge on the thing.
What's the significance of knowing oxidation states?
What's the significance of knowing the oxidation states? The thing is, when we look at something like nitric acid, nitrogen dioxide, and water, we can't tell by looking at ionic charges if electrons have been lost or gained, because there are no ionic charges. They're not ionic compounds. And so we do know that, like, when carbon reacts with oxygen, it's a combustion reaction, and all combustion reactions are redox reactions. But how can we tell which one's being oxidized and which one's being reduced? So oxidation states is a technique to help us identify, especially for the nonmetals, what's being oxidized and what's being reduced. Because what we see when we look here is that the nitrogen started out with an oxidation state of +5, and now it's only +4. So this went from +5 to +4. Is that oxidation or reduction? It's reduction.
Because it gains.
It gained an electron going from +5 to +4. So reduction is gain of electrons. Or reduction is a decrease or a reduction in the oxidation state. Oxidation is an increase in the oxidation state. Oxidation is a loss of electrons. So we have a reduction. There must be something that's being oxidized. What is it? Tin. So tin went from 0 to +4. It had an increase in its oxidation state. It lost electrons. And so this is the oxidation. So we look at this and we say that the tin is being oxidized and the nitrogen is being reduced. And without looking at oxidation states, I dare you to figure out how it is that it's the nitrogen and not the hydrogen or the oxygen. The tin is easy. You don't have to look at oxidation states for that. But the nonmetals can get very tricky without oxidation states. Any questions? Yes?
Like the hydrogen and oxygen being spectators?
Are the hydrogens and oxygens spectators? Well, in terms of oxidation reduction, yeah, because they are not undergoing oxidation or reduction, but they are participating in part of the chemical reaction, and so we don't refer to them as spectators in the same way that we do for spectator ions. Because, here oxygen was covalently bonded to nitrogen, and over here 2 oxygens still are, but one of the oxygens has now left that molecule and has bonded with hydrogen instead. So there is chemical change involved for those, even though they didn't undergo redox. Any other questions? So oxidation and reduction must occur simultaneously. If something loses electrons, something else must take them. There's no shelter where you can drop off your unwanted electrons. So the reactant that reduces another element is called the reducing agent. The reducing agent then contains the element that is oxidized. And if I were you, I'd be thinking, wasn't this confusing enough? Why are we doing this? I'm sorry, it is confusing. So let's think of it this way. Let's think about Hollywood and about movie stars and their agents. Okay? So, does the movie agent star in the movie? No. Who stars in the movie? The movie star, right? The agent arranges for the movie star to be in the movie. The reducing agent causes something else to be reduced. It's an agent of reduction. That's the best I can do. The oxidizing agent isn't oxidized. It causes the other thing to be oxidized. So if the oxidizing agent is causing something else to be oxidized, that means the oxidizing agent is being reduced.
I get it. That's easy.
Okay, somebody got it. Yes. I think usually nobody gets it. If you can get your brain around it, it's not that bad. You throw the word agent on there, and it's the opposite of what you think, basically. Okay, so what do we do with this? So this question's asking, first, determine whether or not each reaction is a redox reaction, because not all reactions are redox. And if it's a redox, identify the oxidizing agent and the reducing agent. So let's look at this first one. Is this a redox reaction? I hear no and I hear yes. What are we going to look at to see if it is? Well, first of all, here we have a metal and a non-metal element reacting to form an ionic compound. That's going to tell me it's a redox reaction. But then let's also look, since we have an ionic compound here, let's look at charges and see if anything is changing charge, because that would indicate that electrons are being gained or lost. Personally, I think it's a good idea to look at charges first and only go to the oxidation states if you need to. So what's the charge on lithium here?
0.
It's 0. So that has a 0 charge. And how about the chlorines? 0. Okay, here we have this ionic compound, metal, non-metal. What's the charge on the lithium in the compound? +1. What's the charge on the chlorine? -1. Did lithium lose an electron? Yes, it did. That's the only way that it can go from being a lithium atom to a lithium ion. It loses an electron.
And we're saying that the first two are 0 because they're by themselves.
Right.
And then the other two is like after they like.
Right. And so we can tell this doesn't have a charge. If this was an ion, if this was lithium ion, the charge would have to be shown.
Okay.
The only time we don't show charges that are there is in a compound. This isn't a compound. It's only just Li. So this has no charge. Anytime you have just an element and there's no charge written, the charge is 0. So we've got the lithium going from a 0 to a +1. So we know that the lithium lost an electron. Oxidation is loss of electrons. So this is oxidation. So what kind of an agent is it? It's a reducing agent. It's a red agent, the reducing agent. It lost electrons, it was oxidized. It is causing the reduction of something else. So if there's oxidation, there must be reduction. What's being reduced? The chlorine. The chlorine's going from 0 charge to -1. You do that by gaining an electron. So for the chlorine, it gained an electron. Reduction is gain, Rig. So this is reduction, and so that is the oxidizing agent.
So it's basically like when you're describing it, it's one way and then you flip it when it asks for it.
Yeah. So I can say lithium is being oxidized. Chlorine is being reduced. Another way to describe it is lithium is the reducing agent, chlorine is the oxidizing agent. And they're just backwards of each other. And all these words that I'm saying when we're looking at this, that's what I would encourage you to do when you try to solve a problem like this. Because it's so easy to get it backwards, right? It's 50-50 chance. And if you're just going to guess, then just guess and don't even bother with it. Let's look at number 2. Is this an oxidation reduction reaction? Yes, it is. Here we have aluminum as an element with no charge, and it's becoming aluminum 3+, losing electrons, right?
So it goes from 0 to 3+.
It goes from 0 to 3+. So the aluminum here, losing electrons is what? Oxidation. So that's oxidation. What's happening to the tin? Going from 2+ to 0. Reduced. So that's the reduction. So they're asking us for the oxidizing agent and the reducing agent. Which is the oxidizing agent? The tin, 2+. And the reducing agent? Aluminum. Now, like on a mastering chemistry question, if you put tin with no charge, that would be wrong. It has to be one of the reactants. So aluminum is the reducing agent, tin 2+ ion is the oxidizing agent.
So we always do the ones in the reactant?
Yeah, it's the reactants. And over in the products, this is the result of after the oxidation and reduction has occurred. Number 3.
This makes more sense than like doing the charges themselves, like adding the 0 and all that.
Okay, well that's good. Number 3, is this a redox reaction? You're like, there's all this stuff in there. Let's look at it in terms of ions, because here we have an ionic compound, and here we have an ionic compound, ionic compound, right? Let's look at the ions and see if any of them are changing charges. So what are the 2 ions in this first reactant? You might want to think of it this way, well, one of them's NO3-, and then the other one's Pb with some charge. What's the charge? 2+. And then in lithium chloride, what are the 2 ions? Lithium with what charge? +1, and chloride with what charge? -1. And here we have PbCl2. So we've got lead and chloride, and what are the charges? 2+ and minus. And the last one, lithium nitrate? Plus and minus. This is stuff we learned in, I think it was chapter 3. Is anything changing its charge? No. There's no transfer of electrons in this reaction. This is not a redox reaction. What kind of a reaction is it? Precipitation reaction. Here we have 2 soluble aqueous solutions of ionic compounds. And in the products, we have a solid ionic compound and an aqueous. But this solid here tells us that's a precipitation reaction. So the good news is we don't have to identify any agents in there. How about the last one? Yes, that's a redox reaction. We have a nonmetal reacting with oxygen. That's a combustion reaction. It's always going to be a redox reaction. How do I identify what's being oxidized and reduced? Can we look at charges here? No, there's no metals, right? So we're going to have to do oxidation states. What's the oxidation state of carbon? 0. How about oxygen here, O2? 0. They're elements. Okay, and then we go over here to the carbon dioxide. We think Fa765, no fluorine, no hydrogen, oxygen. Oxygen gets to be -2. What's the carbon? +4. Okay, so the carbon goes from 0 to +4. What is that? Oxidation or reduction? Oxidation. And the oxygen goes from 0 to -2. Reduction. So my oxidizing agent is which one? The oxygen. And the reducing agent is the carbon.
So did you get the -2 because it's usually just a negative charge?
I got the -2 for the oxidation state of oxygen because of Rule 5 for oxidation states.
Okay.
So oxygen is the third priority, but it's the first one we come to in this compound. And so oxygen gets to be -2. Basically, all those nonmetals, if they win the draft, you go down and okay, you get your first choice, they're going to choose the same number as they would if they were an ion. So oxygen is going to be -2. Any other questions? Let's look at combustion reactions a little bit more. So combustion reaction is characterized by a substance reacting with oxygen to form one or more oxygen-containing compounds. And this often includes water. Combustion reactions also emit heat, and so we utilize them a lot in our daily lives to generate heat. Example is natural gas. I have a gas stove at home. When I light that guy up, I've got this reaction going on. Methane reacting with oxygen from the air to form carbon dioxide and water. We look at this and we see a substance reacting with oxygen, and it's forming compounds that contain oxygen. It's a combustion reaction. Combustion reactions are also redox reactions. And if we look at the oxidation states here, we've got a -4 for carbon and a +4 for hydrogen, and we've got 0 for the oxygen. In the products, the carbon has gone from -4 to +4. The carbon is being oxidized. The oxygen is going from 0 to -2 in both of those. The oxygen is being reduced. The hydrogen is not undergoing redox. Any questions?
Can we memorize some of these? Like,
Well, you can memorize characteristics of the different types of equation or reactions. Like you see something reacting with oxygen, that's combustion, which is also redox.
no, I mean like the individual parts themselves. So like CO2 is like that will always be the +4 and then the -4.
Well, in CO2, it will always be +4 and -2, and you could memorize those, but that's an awful lot of memorizing. I think it's better to memorize the list of rules and just apply the rules. Let's write a balanced equation for the complete combustion of liquid ethanol, C2H5OH. Well, obviously, the C2H5OH is going to be one of the reactants. Yes?
I just want to make sure on the last slide, like the carbon was being oxidized, right? And the oxygen was
Being reduced. Mhm. So here we have this ethanol, and we're told that it's a liquid. We need a balanced chemical equation. We need a reactant, another reactant. It doesn't tell us what the reactants and products are. Combustion. You need oxygen for things to burn. So the other reactant is always oxygen. And oxygen is a diatomic element, and so it's always O2. And we should understand that oxygen is a gas. And that's going to form. When you have hydrocarbons or substances such as this that just contain carbon, hydrogen, and oxygen, they're going to produce carbon dioxide and water. Those are the products. So you just remember that. So the products are CO2 and H2O. Well, what's the state of carbon dioxide? Gas. What's the state of water? We might want to say liquid. We're burning something. It's going to be hot. It's a gas. Have you ever noticed, you go, if you have a gas stove, if you have an electric, it's not going to work. If you have a gas stove and you put a big pot of tap water on there, you're going to make spaghetti or something, and you turn on the burner, and what do you see on the outside of the metal pot right after you turn on the stove? Condensation. All of a sudden there's the outside of the pot gets wet. What's going on with that? That's the water from the combustion reaction. In the combustion reaction, it's given off in the gas state, but as it hits the cold pot, it condenses. As the pot begins to heat up, it evaporates off again. But there's your evidence that, yeah, water is given off in a combustion reaction. Seems a little funny because here we have something burning and it's giving off water, and we use water to put out fires. But
Go ahead. I was just thinking about like distilling it. Like if all you have is gas, you can distill the water out of it by burning it.
you could get water that way, yeah. Yeah. Okay, so what do we need to do now? We need to balance it. So let's just do this by inspection. And I am seeing that oxygen is all by itself. That tells me I probably should leave that one for the end. And I'm going to look here, and I've got 2 carbons on the left side. I only have 1 on the right. So I can fix that by putting a 2 in front of the CO2. And I decided to leave oxygen for the end, so now I need to take care of the hydrogens. Here I have 5 hydrogens and 1 hydrogen. The reason that those hydrogens are not written together is because OH is a functional group. This is one of those organic compounds that we just kind of briefly talked about. There's a reason that it's written this way. But there are a total of 6 hydrogens there. So then I need 6 hydrogens on the right side. So if I multiply the water by 3, that'll get me 6 hydrogens. Now I need to look at those oxygens. So on this right side, I've got 4 oxygens in this first one, and I've got 3 in the second. So I've got a total of 7 oxygens over there. And on this side, I have 1 oxygen, and then I have 2 oxygens there. If I multiply this by 3, that's going to give me 7. So I need 3 O2s. Any questions? End of chapter 4, finally.